So last time we looked at this example. This is the right recursive version of the grammar, and these are the first and follow sets that we computed last time. So now the question is, given these first and follow sets, how can we check if this grammar is LL1 or not? So it's LL1 if it's parsable using the LL1 parsing technique. And the LL1 parsing technique, is it a top-down or a bottom-up? It's a top-down technique. So it starts from the start variable, and it will start looking for substitutions or expansions. But LL1 parsing works only if what? It works only, yes?
What's the condition for when it works?
So when does LL1 parsing work? What's the... Yeah.
If all the firsts don't have an epsilon, and if it does have an epsilon, then the intersection of the first and the follow must be disjoint.
Okay. So only, on a high level, only if there is only one substitution is possible or is valid. There is only one valid substitution or expansion of the current non-terminal that we are trying to expand. If there are multiple valid expansions, then LL1 will not work. There has to be only one. And there is one if we have this condition. So we should have this condition satisfied for every production of the form A equals beta 1 or beta 2 all the way to beta n. If we have a production with multiple alternatives, or in fact multiple productions, then the first sets of these should be disjoint. And not only that, if one of these has an epsilon in its first set, we should also look at its follow set. So we look at the follow set only if the first set has an epsilon in it. And what's the rationale behind this? Why do we look at the follow set only if the first set has an epsilon in it? Yes?
Potentially disappear.
It can potentially disappear. So what's the point in looking at the follow set? Yes?
You look at the follow set because it's what comes directly after.
Yeah, because it comes directly after it. So when I choose to substitute an epsilon for this, this means that I'm not matching with anything in the input string. I'm trying to match symbols, the grammar symbols, with the string in the input. And if I substitute an epsilon, this means that I'm not doing any matching at this point. I'm skipping the matching or deferring the matching until a subsequent step. And that matching will be possible at a subsequent step only if the follow, if what I'm seeing in the input, if what I'm currently seeing in the input belongs to the follow set of this. So if I'm seeing an A in the input, my pointer is here. So what comes after B2 has to have an A in it. If A is not a possible follower of this beta 2, then I know that this is not a valid substitution. Okay? All right. So this is the idea in looking at the follow set. So we write this mathematically as so a grammar is LL1 if for every production the first plus of beta I intersected with first plus of beta j equals should be equal to phi, the empty set, where first plus plus of let's look at the production. First plus of an A beta I equals first of what?
Just a BI.
Beta I if what?
If there's no epsilon in.
If there is no epsilon, if epsilon does not belong to first of beta I, and it's equal to if epsilon belongs to first of beta I, then what's the first plus?
You have to union the follow of A to that.
Yeah, the follow of A union with first of beta I. So it's first of beta I union follow of A otherwise. So these are the rules. So now let's apply this to this grammar here. So we have to check this for every production. Now there are some productions that we don't need to check because they have a single alternative. So this production is already good because it has a single alternative. There's nothing to check. Here there is a single alternative, so we have nothing to check. It's already good. This has two alternatives, so we have to check it. So let's check this. So now we will look at first plus of S goes to A, and first plus of S goes to A. Now the question is, what's the question? Does A have an epsilon in its first set? So the first set of A has a B, it does not have an epsilon. So it's the first set of this is only what? The first set of A. So this is going to be only first of A, which is B. Now, first of first plus of A of SB, well, let's write it here. First plus of SB. Again, the question that we ask is, does B have an epsilon in its first set? B does not have an epsilon in its first set. So the first of this is just the first of B, which is A. First of B is A. So what does this mean? It means that, what do we conclude from this? So they are disjoint. So this is good. So this production is good. Because first plus, so the intersection of these two, so first plus of S goes to A, intersected with first plus of S goes to B. This is phi, which means good. Okay, so we have checked one. Now we should check this. Now first plus of what? Beta, B prime goes to A, C, B, B prime.
Or F's.
Okay, so this is the first alternative. The first plus of this is going to be what? We look at the first of A, and the first of A, does it have an epsilon in it? It does not have an epsilon in it, so all what we have is a B. Why? Because first of A does not have an epsilon in it. If first of A had an epsilon in it, we would have looked into first of C, and so forth. And if all of them had epsilon, if there is, if the first of all of these had epsilons, then we should look into what? follow of B prime. So if the first sets of all four has the first sets of all of these four have epsilons in them, then we should look into B prime. But this is not the case here. We only look at B because this does not have an epsilon. So we stop here. Now, first plus of what?
Epsilon.
Yeah, B prime goes to epsilon. And in this case, what's the first of epsilon? The first of epsilon is epsilon, right? So it already has an epsilon, so we apply this rule, the otherwise. So now we look at follow of B prime. Now follow of B prime, what's follow of B prime? End of file B. Now what's the intersection of the two?
B.
First plus of B prime A C B prime intersected with first plus of B prime epsilon. This is going to be B. So this is not phi, not equal to phi. So we can stop here. This is enough to say that this grammar is not LL1. Because if you find any intersection between any two alternatives, so these two alternatives are not good. We have two alternatives and there is an intersection between the extended first set of this and the extended first set of this. So it's not LL1. Okay, so only one non-empty intersection is enough to say that this grammar is not LL1. Now let's continue just for the, we don't have to continue, but let's continue for the sake of illustrating how this procedure works. Okay, now we should look at what? These two alternatives for C. So first plus of C goes to AD. What's the first plus of this? The first of A, which is a B, and it doesn't have an epsilon in it, which simplifies things, so it's a B. So it's first of A, which is B. Now first plus of what? C goes to epsilon. This is going to be, this is already epsilon, so we should look at follow of C. And follow of C is B. So again, we have a problem. The intersection is B. So and the intersection is B of these two, which is not good. Again, not LL1. One non-empty intersection is sufficient to call it non-LL1. Last, so this is not good. Now how about D? Let's do D. First plus of D goes to BC. So the first of B is A, which is A. And the first plus of D goes to BC. What's the first plus of this?
Just B.
Just
B.
B. Because this symbol is a terminal, and the first of a terminal is the terminal itself.
Yeah.
Okay, so the first of this is B. So now the intersection between A and B is what?
Nothing.
Phi. So the intersection is phi. Which means that this is good. But we have two problems. So this is good. This is not good. This is not good. And this is good. So what does this mean?
It's not good.
It's not LL1. Okay. Okay. Any questions on this procedure? Yes.
I have one question. I remember in the last lecture you said like if it wasn't LL1, we could rearrange it to become LL1. I know this is like a bad example, but let's just say that we had some grammar and like we did this algorithm.
So I didn't say that we can restructure it so that it's LL1. I said we may be able to.
Okay.
So we may be able. Not every grammar in the world is LL1. So some grammars are LL1, some grammars are not.
Okay.
And if the grammar in its current form is LL1, we may try to do certain things like left recursion elimination and left factoring that we will be studying today. We will be trying to do transformations like this in the hope of transforming this into an LL1 grammar, but we may or may not succeed.
Okay.
We're not guaranteed to succeed because not all context-free grammars are LL1 grammars. Okay. In fact, it's not possible. The problem of determining if a grammar is LL1 or not, it's an undecidable problem, which means that you cannot come up with an algorithm that will take an arbitrary grammar and tell you whether it can be transformed into LL1 or not, or it takes a language and determines if that language is LL1 or not. So meaning taking a grammar and determining if we can transform that grammar to an LL1 grammar or not, you cannot come up with an algorithm. So it's not always possible to even determine if it's LL1 or not. You may try. Sometimes you succeed, sometimes you don't succeed. But for many language constructs, you can transform the grammar into an LL1 grammar, and you can successfully use the LL1 parsing technique to parse it. So you have the set of context-free languages, and LL1 is a subset of this. So the languages that are parsable by LL1, the set of languages that are parsable by LL1 is a subset of the set of languages that are parsable by the set of context-free languages. Okay. And the technique that we will be studying in the next lectures, which is LR1, that's more general. So it parses a larger set of languages. So LR1 can parse a larger set of languages. Now, where are regular languages here?
Subset of LL1.
Yeah, they're a subset of LL1. So regular are here. Regular are easily parsable. You don't even need grammars, right? You don't even need context-free grammars. You can recognize a regular language using a finite automaton. So regular languages are much easier. But context-free languages, a subset of them is recognizable by LL1. A bigger subset is recognizable by LR1, which we haven't studied yet. And there are other parsing techniques. So any questions on this? Okay. So I'm going to comment on the procedure or the algorithm that we have described last time for computing the follow set. Okay. I don't think we need. well, let's keep them anyway. So for computing the follow set, we looked at a production of the form x is alpha y a1 a2 through an. So to compute the follow set for y, we have to look at a1 a2 through an. And we start from y, and we look at a1. So let's look at a more concrete example. X is alpha, y, a1, a2, a3, a4, a5. Okay, or let's put some space. I'll just rewrite them, but with more space. A2, A3, A4, A5. Okay, so now the procedure that I described last time, when we want to compute the follow set of y, we look at A1 and ask the question,
Does it have an epsilon?
yeah, does it have an epsilon? So if it has an epsilon, we look at first or follow of A2? First of A2. So we're saying, okay, if this is an epsilon, this has an epsilon in its first set, we look at A2. And if A2 has an epsilon, we look at the first of A3. And if all of them have epsilons, then we look at follow of x. We add follow of x to follow of y. Okay? Now, the procedure that I described last time, or which is what I'm just redescribing right now, is not efficient. Why isn't it efficient? Do you see where it's not efficient?
Computing the first of A1 involves computing the follow of A1.
Yeah. Okay. So, well, we assume that all the first sets have been computed already. All the first sets have been computed already. So we are only computing the follow sets here. Yes.
So if you don't have the complete follow set of x yet,
Yes.
then you have to go through another iteration to get the follow set of x if you need it.
Okay. Well, the follow set, yes. So that will always be the case. So yeah. So this is dependent on the follow set of x, and yeah, if in the current iteration the follow of x is not complete, we'll have to go through another iteration. But think about A1, A2, A3, A4. So these could be, of course, they could be terminals or non-terminals. But assuming that all of these are non-terminals, I will need to compute the follows of A1, A2, A3, A4. So I need to compute the follow sets for all of them. And with this procedure that I'm describing, in order to compute the follow set of y, I will have to scan all of these. If all of them are epsilons, I will have to, in the worst case, I will have to scan all of these. Then when I go to compute whether it's after or before, when computing the follow set of A1, I will scan all of these. And when I compute the follow set of A3, I will scan all of these. So there is a lot of duplication in scanning the follow lists of this. Now, in the book, there is a more efficient algorithm that avoids scanning this multiple times.
Yeah.
It can scan the list only once by scanning backwards.
Yeah, so I was just thinking myself, it start at A5, then go A4, A3,
Okay.
go backwards.
Yeah, so the algorithm that I described last time is conceptually easier to understand, but it's less efficient. What is more efficient is the algorithm in the book, which scans these backwards, and in one scan, it updates the follow sets of all non-terminals. So if in this example, if we have A1, A2, A3, A4, assuming that this is an epsilon and this is no epsilon, it doesn't have an epsilon, and this is an epsilon and this is an epsilon. So in this case, what will be the follow of A5?
And the file.
Follow of x.
Follow of x. Yeah, exactly. Follow of A5 is going to be the follow of x.
Okay.
Now, what will be the follow of A4?
First of A5.
First of A5 plus follow, union follow of x. So it's going to be follow of x, union first of A5. And what's follow of A3? The follow of A3 is going to be follow of x,
Follow of x.
union
First of
first of A5, union first of A4. Okay, so what does this mean? It means that we keep accumulating. So the follow of A3 is going to be, if we start from follow of x and we keep accumulating the first set, in fact, we have to subtract the minus epsilon here. Minus epsilon and minus, you know this. We don't add the epsilon. So it's the first minus the epsilon. But we have to keep accumulating. But when we get to A3, which has a non-epsilon in it, now what's the follow of A2?
it's just the first of A3.
Exactly. So the follow of A2 is just the first of A3, because this is a non-epsilon, which means that when we expand this, there will be at least one terminal in it, and the first of A4 and A5 cannot follow A2. So the first of A2 is going to be, the follow of A2 is going to be the first of A3. And then the follow of A1 is going to be equal to first of A3 union first of A1 is going to be first of A3 union first of A2. Of course, minus epsilon. Everything here is minus epsilon minus. So the algorithm in the book is based on scanning from the last symbol in the production. You initialize, you have a, what they call in the algorithm, they call it a trailer. So the trailer is initially the follow of x, and you keep accumulating in that trailer the first sets as you scan. You keep accumulating, but you stop accumulating when you get to what?
Something that does not have an epsilon.
Yeah, exactly. When you get to something that does not have an epsilon in it, you stop accumulating.
Now the question.
Yeah.
Question. Where does the epsilon have to appear in say A1? Is it in the first set or follow set or anywhere?
No, this means the first set. So this epsilon means A2 has an epsilon in its first set. So the follow set, it does not make sense for the follow set to have an epsilon. Okay. So you can't say that something is followed by nothing. It has to be followed by something. And that something could be the end of file. So if it's not followed by any other symbol, then it's followed by the end of file. So it never makes sense for something to be followed by an epsilon.
Or it's just an empty set.
Well, the epsilon is, yeah, it's not, it cannot be followed by an epsilon. So it has to be followed by a terminal or an end of file. So when you look at a string, okay, when you look at a string, A, B, X, Y, Z, A, B, C. So every symbol in this string is followed by something, except the last one, it's followed by end of file. Nothing is followed by an epsilon. Okay, so now let's, so now the you know, the algorithm in the file is the algorithm in the book is based on computing this trailer. You initialize it to follow. You keep accumulating first, and when you get to a variable that does not have an epsilon in its first set, you basically reset trailer. You reset it to first of this variable that doesn't have an epsilon, and then it starts accumulating from that point, and when it gets to another non-epsilon, it resets again, and so forth. Okay, so please go through the algorithm in the book, the algorithm for computing the follow sets in the book. Any questions on this? Okay, so let me now we can leave this. Now let's rewrite the classic expression grammar. Expression is expression plus term, or expression minus term, or term, where term is term times factor, or term divided by factor, or factor. And factor is identifier, or number, or expression. Now what if we, yes?
Why don't we write expr is term plus term, or expr is term minus term? Why expr plus term?
Why expression plus term?
Because I'm pretty sure it would still work the same if you said expression is term plus term and not expression plus term.
But then you cannot recur. How can you recur? It has to be recursive. So if it's term plus term, you are limiting this to only 2 terms. So how can you have an expression with more than 2 terms?
Yeah, that would work.
So the whole point is to have the recursion, so that the expression can have an arbitrary number of terms. Okay, so now we would like to add array elements and function calls to this. And array elements and function calls, when you have an expression like this, x equals 2 times a of 5 plus 3. So in this case, what's a of 4? The array access, the array reference. So where does it fit in the grammar? So is it a term or a factor?
A factor?
It's a factor, right? It's a factor. It's not a term. Because you can multiply by this array, and you can divide it. And so it's just a factor. So it's treated like an identifier. It's like a variable name, but this is a variable name with an index. And here, inside of this, you can have an expression.
Yeah.
So it's to add support for array references. It's identifier bracket expression bracket. So this will add arrays with an array with an index. So you can a factor can be an array, and a factor can also be a function call, like x equals 3 times f of y and z, and x or a or whatever plus 3. So again, the function call could be another factor. Okay? So we can add this by, again, saying, or we can have an identifier with open parentheses, close parentheses, but what do we have inside? So is this an expression? Yeah, expressions with commas. So it's an expression list. Let's call it expression list. The expression list is the list of expressions with commas. By the way, this can be an expression because you can say in C-like languages, f equals 5 times x plus 3. And so this, all of this is one parameter. Right? So this expression is a parameter. The second parameter is z. And the fourth parameter is 5 plus 9 divided by 4. You can do this. So each parameter can be an expression. So what's inside here is an expression list with commas. So how we need now to define an expression is already defined, but an expression list we need to define it. And how do we define an expression list?
Expr list, comma, wait, no, expr, comma, expr list, or expr.
So we need to do some recursion, right? So we need to do, it's a recursive rule because we are not setting a limit on the number of expressions that an expression list consists of. So we're not setting any limit on the number of parameters that a function can have. So this can be, we can use left recursion and then eliminate it. So it's expression list, expression list, comma, expression, or expression. Of course, this assumes that we should have at least one expression. If you want to accept something like function call with empty, you can easily add an epsilon. So you can do the expression list could be this or an epsilon. So you introduce another variable here, which is an expression list with one expression or an epsilon. This is one way of doing it. So you can accept the epsilon using different ways. So there are different ways of accepting an epsilon here, an empty list of expressions. But this, what is on the board, does not accept. It does not accept an empty list of expressions. So you have to have at least one expression in the list. Okay, so it will be, a trivial change to make it accept an empty list. Now the question is, this is left recursion, so we can transform this into the right recursive form. Now in doing that, so this is left recursion. So this is our x, and this is our alpha, and this is our beta. So we can write this in the right recursive form. Expression list is expression list prime, and then expression list prime is
Comma.
comma expression what?
Expression list prime.
Expression list prime
Or epsilon.
or epsilon, exactly. So now we can get rid of the left recursive form. Okay, so we replace the left recursive form with the right recursive form. I'm just doing this because it's usually more intuitive to write the left recursive form and then convert it to the right recursive form, but you can write the right recursive form directly. Okay, so now we have support for array references and function calls. Now the question is the grammar on the board LL1?
No.
Obviously it's not LL1.
I think it's L2.
Well, the question is it LL1?
No.
Why isn't it LL1?
Is it a factor? If you just look ahead one, see an ident, you don't know if it's the first alternative or if it's an array index.
Exactly.
Yeah. So we have this common factor, which is the ident. So the identifier is common. So if you compute the intersection of this alternative and this alternative, it will have identifier in it. And if you compute the intersection of any pair of these three alternatives, this 1, 2, 3, you will have an identifier in it. So there is an obvious intersection. The intersection is obviously not phi. But this is, this is a kind of intersection that we can easily eliminate by doing what we call left factoring, which is like, factoring in math. So this is a common factor, right? So we can do, we can transform this factor into factor is. So we will put number or expression or identifier, which is the common factor. Then its identifier what? Identifier something. So this something we call it factor prime or something. Or maybe factor prime is not a good name. Factor, let's call it factor prime. Doesn't matter. Factor prime. So factor prime is going to be what?
Extra in brackets or extra list in parentheses.
So factor prime, so this is an identifier followed by an epsilon. This is an identifier followed by this thing. And this is an identifier followed by this thing. So it's an identifier followed by this thing. And this thing is either an epsilon or a bracket expression or parentheses expression list. So we have, this is the common factor. So we put the common factor here. And then it's followed by something. And this something has multiple alternatives. But these multiple alternatives do not have a common factor. Assuming that, so these alternatives will not have a common factor. Under what condition? Yeah.
The follow of factor prime doesn't match the other.
This or this.
Yeah.
Exactly. Yeah. So there will be no common factor. If the follow of factor prime, because for this is an epsilon, it has an epsilon in its first set. So the first plus of this is going to be the follow of factor prime. So as long as the follow of factor prime does not have this or this, then it's there is no common. And in fact, in this, if you go back to your factor prime, the follow set, well, we have not computed the follow set of factor prime, but the follow set of factor prime is going to be the follow set of factor, and the follow, because it's the last thing in a factor, so the follow set of a factor does not have an open parentheses or open brackets or open parentheses, because a factor cannot be. So go back to your follow of factor, it will not have any of these in it. Okay, so this is what we call left factoring. So generally speaking, so in general, left factoring, if we have an x that goes to, let's say, alpha beta 1 or alpha beta 2 all the way to alpha beta n, or gamma 1 or gamma 2 or gamma what m, right? The number of gammas does not have to be equal to the number of alphas, of the betas. So with left factoring, this gets translated, or this gets transformed to x goes to what?
Alpha.
Alpha something x prime or gamma 1 or gamma 2 all the way to gamma m, where x prime is
Beta
Beta 1
1.
and beta 2.
yeah, beta 1 or beta 2 or beta n. So this is left factoring. This is how we applied it here. This is what left factoring is in general. Whenever you have a common factor, a common prefix, and the prefix doesn't have to be, you can apply it to any prefix. Doesn't have to be a single symbol. So you can apply it. You take the common factor followed by x prime, and x prime takes care of these alternatives. Then the rest of the grammar, if you have other alternatives that don't have a common factor, these just remain the same. So the gammas remain the same. So in this example, where are the gammas here?
Number expression.
Number and parentheses expression. So this is gamma 1, and this is gamma 2. And this is alpha 1. This is alpha, 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 and this is beta 2, beta 3, and this is epsilon is beta 1. Okay, so this is left factoring. So left factoring is another technique that may help you transform a non-LL1 grammar into an LL1 grammar. Sometimes it works, sometimes it doesn't work. So it's not guaranteed to work. So we have two tools. We have studied two tools, left recursion elimination and left factoring. Okay, any questions? Okay, so now I think you have all the material that you need to do the assignment number 2. Any questions on today's lecture?